Thank you very much, Gwendolyn, for this introduction. And indeed, I'm studying highly accreting young stars, also known as young eruptive stars. I'm studying these objects at various wavelengths from the X-ray to the radio. But today, of course, I'm going to focus on the thermal infrared regime. To give you a very brief introduction, I would like to remind everyone that accretion during star formation is not a smooth process. It is not even smoothly decreasing. In reality, accretion varies by several orders of magnitude. And how do we know this? There are indications for this from numerical studies. For example, here on this graph, you can see the mass accretion rate as a function of time from the results of hydrodynamical simulations done by Eduard Vorobyov and collaborators. If you are interested in these numerical and theoretical aspects of accretion, I encourage you to read his papers or some more recent publications by my colleague Kundan Kadam. But you can see here in this graph that there are very brief episodes of strongly increased accretion rate, which are very similar to what we observe during the eruptions of FU-Orionis type stars, or shortly FUors. So these are basically the observational evidences, these eruptions of young stars that we can observe. Here we can see some light curves of these objects. So young eruptive stars brightened by several magnitudes, up to 5 magnitudes at optical and infrared wavelengths. And then there are some of them which show a shorter repetitive outbursts, but FU-Orionis, the prototype, and the other objects that belong to this class stay in the bright, high accretion phase for several decades or even a century. They reach peak bolometric luminosities up to several hundred solar luminosities. And of course, these very powerful outbursts induce important changes in the disk, especially in the terrestrial planet-forming zone. These outbursts affect the geometrical structure of the disk. They can induce mineralogical or chemical changes in the disk material. FUors may also affect the immediate surrounding of these young stars because enhanced accretion is often accompanied by enhanced mass loss, mass outflow. And basically these recurrent outbursts eventually may clear up the environment of an embedded young star. So fewer outbursts may drive a very young embedded object towards a class 2, a T Tauri phase. And accordingly, we can find fewer outbursts in objects which are less evolved, more embedded, and they show, for example, the 10-micron silicate feature in absorption. But we can also find fewer outbursts in more evolved, almost disk-only sources, where we have a direct view of the disk surface, and these objects obviously show the 10-micron silicate feature in emission. So this outlines a kind of an evolutionary sequence that is driven by the eruptions. In the past decade, several new young eruptive stars were discovered, but their status in this evolutionary sequence that I just showed you is not always quite clear. So we targeted 5 newly discovered young eruptive stars, young FUors, and we took 10-micron low-resolution spectra for them with the VISIR instrument on the VLT over a few observing semesters. Here you can see an overview of our results. You can see that some objects we observed twice, some of them we observed only once, and we complemented the sample with V346 Normi, which you observed with VISIR earlier for another project, but it also belongs to the FUor class. As a simple analysis, we fitted the observed 10-micron features with different templates. We used, for example, the spectrum of the comet Hale-Bopp, which is dominated by crystalline silicates. And we also used the spectrum of ISM, the interstellar matter, which is dominated by small amorphous dust grains. And we also used the spectrum of FU-Ori, the prototype of the class. which, according to the modeling mineralogical decomposition of Sasha Kwans and collaborators, contains about half amorphous olivine, half amorphous pyroxene, and more than 80% of the grains are larger than 1 micrometer. So these are large amorphous grains. And apart from the absorption objects, which are most consistent with the ISM template, all the objects that show emission, they are most similar to FUors, so they contain large amorphous grains. To quantify this a bit more, we complemented our VISIR sample with the FUors that had been observed earlier with the Spitzer IRS, and we normalized the spectra with the continuum flux. So these are the normalized, continuum normalized spectra ordered according to the feature strength, with the strongest feature at the top and the weakest feature at the bottom. So we can characterize the feature strength by measuring the S peak, which is the peak value of the feature. And we can also characterize the shape of the feature by dividing the continuum normalized value at 11.3 micron by the continuum normalized value at 9.8 micron. Why do we care about the feature strength and the feature shape? Well, Gwendolyn yesterday gave us a very nice overview of dust processing. We know that dust processing changes the strength and the shape of the 10 micron silicate feature. And if you look at this graph, where I plotted the feature shape as a function of feature strength, you can see that, for example, grain growth or increasing crystallinity moves a data point in this graph at various directions. And what is interesting in this graph is that normal, non-eruptive T Tauris and Herbig AB stars, which are plotted with the gray circles here, show a wide variety from the small amorphous grains to significant grain growth and even crystallization. On the other hand, FUors show less variety. They all have amorphous, mostly large grains. We can draw two surprising conclusions from these findings. Well, first of all, it's surprising to find large grains in disk surfaces, as they should be settled in the midplane. So we don't have a definite explanation for this, but we can theorize that maybe these objects have stronger turbulent mixing or stronger winds due to the outburst, and that prevents basically settling. It is also surprising to find no crystalline silicates in FUors, as we would expect that at least part of the grains should have been annealed because of the heat of the outburst, because of the increased temperature. Here we can think that maybe they lack crystalline silicates because the dust has not settled to the disk midplane. So to give you a context, Watson and collaborators found that the increase in crystallinity is linked to dust settling to the disk midplane. So this is where we stand now with the VISIR results, but there are of course very interesting new prospects. For example, MATIS is already operational, and with MATIS, with interferometry, we can resolve the 10 micron emitting region, and we can study dust composition and its radial distribution in disks. And if you're interested in MATIS results for young eruptive stars like for FUors or others, you can rewatch the talk given by my colleague Peter Abraham yesterday, or you can listen to my other colleague Fotini Liku tomorrow. And of course, we are all eagerly awaiting GWST. With MIRI, we will be able to not only measure the 10 micron silicate feature, but also look for colder silicate features, especially cold crystals. And that gives us a very intriguing possibility, because if we can find cold crystals in FUors, that would explain not only why we don't see hot crystals in these objects, but it would also help us understand why we can see in icy cold comets materials that had formed in hot environments. And that was it. Thank you very much.
Okay, thank you very much, Agnes. So I've already found one question. No, there are already two in the Slack channel. The first one is by Mario van den Anker. Do the FUors which show 10 micron absorption features have higher accretion rates compared to the ones which have emission? or is it due to the disk geometry?
I think it's mostly due to the geometry. So the objects that have absorption are typically more embedded. They have a much larger infrared access, and then in those cases we can be sure that we are seeing the central object through a thick envelope.
Okay, thank you. And another question by Alexis Matter. Is there a chance that the 11.3 feature is contaminated by PAS in the FUor systems?
In most cases, probably not. I know of one object which is called Parsamian 21 that shows pHs, very, very strong PA features. For the others, it's not really apparent. I would say it's basically non-existent. So in our study, we didn't do a very detailed mineralogical decomposition, so I wouldn't quantify this. But for example, in the Quancelal paper, there's a modeling of FUorinis, the feature of FUorinis, and then they didn't need any pHs to reproduce, to model that feature. So probably there are no PAs in these objects, which is interesting because luminosity-wise, these objects are more similar to Herbig stars than to the low-mass T Tauri stars, despite being low-mass stars themselves.
Yeah, that's very interesting. Could you pull up your slide number 6 again? While I
Yes.
That one, because I was wondering, so you say that I know it's FUor, I'm sorry, no, okay, never mind. I was just wondering, like, did you compare this, what you found, like, okay, this star is more like crystalline, this is more small amorphous and stuff, your findings, do you compare them with the light curves of these objects? Like, do you, for instance, see like this one has the recent outburst, or
we haven't tried that. Well, partly because some of these objects have very sparsely sampled light curves, but most of them, I think, maybe except for V582 Aurigae, which had an outburst very long time ago. The ones in monocirrus have very recent outbursts, so really they went into outbursts in the past decade. V346 Normie went into outburst in the 70s, I think. The current object, we don't know. I think we only know that it is in the high state itself. So I'm not quite sure whether we would find any correlation with the onset of the outburst. We would certainly need a larger sample, I think, for that one.